In 5, we're asked to work out a couple of limits. This first one, we're going to put the 1 in the 1 in for x and y. You can see you get a 0 in the denominator, but you also get 1 minus 2 plus 2, so you also get 0 in the numerator. And since it told me to evaluate it, I know this limit exists, and so I'm going to try to figure out how to get those two zeros to cancel. And what I'm looking at here, looks like things are going to factor, so let me do that. Try to factor. The bottom's easy enough. It's just a difference of squares, x minus y, x plus y. Top is a little more complicated, but since there's 4 terms, I'm going to try to do it by grouping, and I'll factor an x out of those first 2, leaving me with an x minus y. And then from the second 2, I can see this common factor of x minus y, and my goal is to get that to pop up in the second one. So I better factor out not just a 2, but a negative 2. And what that gives me is a positive x and a minus y. And so now I can factor that x minus y to the top, and I'll be able to cancel it. So let me just write that step. Limit x, y going to 1, 1. And this in the top, I factor that x minus y out. It's going to leave me with x here, and then a minus 2 in that second term. And like I said, I have this x minus y, x plus y in the denominator, and I managed to cancel what was causing the 0 in the denominator. So when I put the 1 and 1 in for x and y now, I get 1 minus 2 is minus 1, and I get 1 plus 1, which is 2. So that limit is equal to minus 1/2. The second part here, when I try to put the 0, 0 in, I do get 0 in the denominator and 0 in the top, but this is telling me that this limit will not exist. And I don't think that's supposed to be there. Sorry, that won't be there on your exam. So when I'm working this one out, I have to use different paths to show that I get different limits. Well, it's easy enough to do x equals 0 and y equals 0, and you kind of look ahead of time. If I let x equal 0, I'm just going to be taking the limit of y squared over y squared, which is going to give me 1. And if I let y equal 0, it's going to be x squared over x squared, which is going to give me 0. So really not much work to do here. You can use the two basic ones. So I'm going to let x equal 0. Along that path, I get the limit x, y goes to 0, 0. Along the path of x equals 0, x squared plus y squared over x plus y squared. Well, when x is 0, like I said, it's just going to knock out those. I'm going to put a 0 everywhere that x appears in my situation here. So I get 0y going to 0, 0. And this top is going to be 0 squared plus y squared. Bottom is going to be 0 plus y squared. That's just 1. And so this limit can be written as the limit as y goes to 0 of 1, which is 1. The other path, y equals 0, it's going to be the limit x, y going to 0, 0. So it's taking longer to write it down than anything. But anyway, this is the proper way to try to say what I'm doing. And here I've got x plus y squared. And now if I let y be 0 everywhere, I get the limit of x 0 going to 0, 0. And letting y be 0 everywhere, I'm going to have an x squared plus 0 over x plus 0. That'll simplify to the following. Limit as x goes to 0, cancel out the x's, and you just get an x there. And this limit will equal 0. Since these two are not equal, that implies that the limit does not exist. In other words, I have two paths where the limit along those paths is not equal. All the paths have to be equal for the limit to exist, and so that's enough to show it doesn't exist, just finding two of them. And there are other paths you could use, but might as well go with the two basic ones if they work. And then number 6 says to find the equation of the plane tangent to this sphere. It's a sphere of radius 3 centered at the origin. Find the tangent plane. Well, remember the way you work this is you could either solve for z, but that makes it a harder problem. But the other option is just leave it as an implicit function. And this would be what we call f over here. And all I need is the partial of f with respect to each one of these evaluated at 1, 2, 2. So partial of f with respect to x is going to be 2x, and evaluate that at 1, 2, 2, and you're going to get 2. Partial with respect to y at 1, 2, 2. Well, again, this is not too bad. That's just 2y. And evaluate that at 1, 2, 2. And you're going to get 4. And partial with respect to z at 1, 2, 2 is 2z. And you're going to get 4 again. And remember, the equation then is your x, your partial with respect to x value times x minus the x coordinate of the point. Then it's your y partial times y minus the y coordinate, and then the z partial. Whoops, put z instead of the actual partial. That's also 4. And z minus the z coordinate. And then you multiply all this out and you get 2x minus 2 plus 4y minus 8 plus 4z minus 8 equals 0. And so combining these, it's 16, 18, and bring it to the other side. I'll have 2x plus 4y plus 4z equal 18. And then I can divide through by 2x plus 2y plus 2z equal 9. So that would be kind of in its simplest form. This is a nice form because I can see the normal vector of 1, 2, 2. And so these partials are giving me that normal vector. But that would be the equation at that particular point.